Hello, welcome back to International Finance. Okay, hopefully at this point you've seen our first lecture that provides a pretty good overview of the course. Now our goal for today will be to review the time value of money. So our last lecture, we did a general overview. You should read chapter 1, which does a pretty good job of introducing the concepts of the international financial system, multinationals, provides a pretty good background of what this course will entail. This week, we're going to review the fundamental concepts of finance. So we're going to do future value, present value, finding the proper discount rate to calculate the present value of future expected cash flows, and amortization, paying off a loan. The way that we're going to approach this lesson, it'll be to kind of make sure that we have a pretty good familiarity with the different ways of calculating present value. So why does this matter? If we go to our equation, the present value equation, on our left-hand side, we have value. And our typical measure of value is probably going to be a stock price or some measure of firm value. And on the right-hand side, in the numerator, we have FCF, meaning the free cash flow. So this is the cash flow that the company has after all of your operations. So you've made some sales, you have some profits that come in, you've paid taxes out, you've made your required investments in operating capital, so your CapEx expenditures. All the cash that's left over is your free cash flow. And that free cash flow is what's paid out to investors. That's going to go to your shareholders in the form of a dividend or be retained within the company as retained earnings, which are all going to be basically for shareholders, or those are going to be paid out to debt holders in the form of your interest and the principal on your loan. So this is really how we think of the investors as having value with the company. Now, in our numerator, we've got our free cash flow, and in our denominator, we've got our WACC, our weighted average cost of capital. And hopefully what you notice in looking at this is that each free cash flow has a little time subscript. So free cash flow 1, free cash flow 2, and you'll notice that in the denominator, 1 plus WACC, 1 plus our discount rate, each of those is taken to the power of 1, 2, all the way up through infinity. So what am I telling you with this equation? First, the time subscripts for the free cash flow, the 1, 2, and all the way to infinity, those are telling you the periods in which these free cash flows occur. You'll notice that in the denominator, where we have our weighted average cost of capital, 1 plus our discount rate, we're raising that to the power of whatever that time period is. So our first period, period 1, it's raised to the power of 1. 2 periods away, 2 years away, 2 months away, 2 quarters away, it's raised to the power of 2, and on and so forth. So for each cash flow, we're finding the appropriate discount rate to take the present value of these cash flows. Now, hopefully we can kind of build on this idea. And what we'll see if we look at a more general timeline, we have our cash flows for each period. So period 0, 1, 2, and 3. And you'll notice the time subscripts. And in between each period, we have some discount rate, some interest rate, I%. Okay, so the tick marks at the end of periods. So time 0 is today, time 1 is the end of period 1 or the beginning of period 2. The reason why we're taking quite a bit of time to establish this idea is because sometimes if we're not super familiar with financial valuations, we'll want to think of the first period as being period 0, but that's incorrect. So we'll do plenty of examples to kind of solidify this idea, but I just want to make sure we're super clear. Time 0 is today. So if this were an NPV problem, then I'd have my first cash flow. Typically, this would be some cost or some payment that I would make to have an investment project. And then in periods 1, 2, and 3, we would have cash flows that we have to discount back in order to get our net present value. We'll build on this as we go through. So our first concept is going to be the time value of money. Suppose your risk-free bank account pays you 5% per year. If you deposited $100 today, in 1 year, you'd have $105. What did we do? Our future value at time 1 is going to equal our present value multiplied by 1 plus our rate of interest, our R. So 100 multiplied by 1.05 yields 105. Very straightforward. Alternatively, If you will receive $105 in 1 year and the discount rate is 5%, what is that 105 worth today? What is the present value of that future value that you'll be receiving? Okay, our present value is our future value discounted. So our future value is going to be the 105, and our present value is going to be what? Our present value is going to be that 105 divided by 1.05. And when we do the math, we'll find that today at time 0, that future value of $105 has a value of 100. Hopefully what you see from this example is that even though in the future I'm going to have 105, because I have to wait, because there is a time value of money, its present value is going to be discounted. So let's do this more generally. If we deposited some P value, some present value at time 0, we want to know the future value at some time T, some period T, same exact formula, but notice something slightly different. So now instead of it being period 1, it could be period 3, period 4, period 5, whatever. If I want to know the future value 5 years from now, I'm going to take the present value and multiply it by 1 plus R to the power of 5. 7 years from now, I'm going to take my present value and multiply it by 1 plus R to the power of 7. In order to get my present value, I can always discount my future value, same logic, same idea. And hopefully, again, what you see is that the time subscript, so future value capital T, we want our time subscripts to line up with our exponents whenever we're using our discount factors. Okay. So suppose I were 10%. After 1 year, 2 years, what would I have? If I were 10% and today I put in $100, after 1 year, I would have a future value of 110. If I want to look at 3 years, same idea. I have my present value of $100, and then I multiply that by 1.10, 1 plus R. In this case, R is going to be 10%. That whole thing to the power of 3, when I multiply them together, I get 133.10. What's important to remember is our order of operations. So we always want to be careful with our order of operations. We want to do the parentheses first, 1 plus R, then do our exponent, take it to the power of 3, and then multiply them together. Okay. So generalizing the approach from the previous slides, we've got our present value equal to our future value at time t divided by 1 plus r to the t. And we can always switch things around. We can very easily solve for our future value. If you give me a present value, I can just move my equation around. All right. What's the present value of $100 due in 3 years if I equal 10%? All right. So we can take this more generally and we can solve for the present value. So in this example, we've got $100, that's our future value. We've got a discount rate of 10%, so 1 plus R, 1.10. And then we also have our time period, N, 3. So again, notice we're going to follow the order of operations. We're going to do our parentheses first. We're then going to take that whole term, 1 over 1.10, to that, raise that to the power of 3, and then multiply that by 100. And as we've established, it should be the case that if I'm getting $100 3 years from now, that today that $100 is worth a little bit less. And in this case, it's worth considerably less because our discount rate is fairly high. It's a discount rate of 10%, and we can all clearly see that it's going to compound through time, and that's true also as we discount. All right, how long will it take you to double your money? Well, in this example, what do I want to know? I want to know how long it's going to take for my $1 to yield 2. So let's set this up and solve for it. On the left-hand side, I've got 2. On the right-hand side, I've got 1. Why? Because I want to double my money. If I wanted to triple my money, I'd put 3 on the left-hand side. I have that multiplied by 1 plus 0.2. The 0.2 is our interest rate that's given in this example. And the thing that I don't know is N. N is the number of periods that it's going to take for my present value to double and to equal what's on my left-hand side. So what am I going to do? Well, I can go step by step, and in doing that, I can take the natural log. The natural log will let my N come down, and now with my N is something that I can easily solve for. That's exactly what I'm going to do. So what do we find? We find when we do the math step by step, and just as a disclaimer, this video is going to be a little bit longer than our videos typically will be, and my hope is that as we work through these, that you pause, you do the math, you approach it yourself, and then at the end of the lesson, the solutions are posted so you can look to see how the solutions are and what the correct way is to approach it. But really, this is so we can all get a good refresher and work through these problems together so that we have the familiarity when we start discussing our discounts, our present values, our annuity formulas, all of it. Okay. So let's keep going. The time value of money, if we have a constant stream of C dollars, so if there's a constant cash flow paid for T years starting next year, well, then we'll have an annuity. So the biggest difference between an annuity and a perpetuity is that the perpetuity is perpetual, meaning that it goes on forever. So we can see that that's going to affect our valuation. So when I look at the present value of an annuity formula, there are two things that should jump out to me. One, if I've got cash flows that are all going to be the same level, so if every single year you're paying me $100, then this is a great formula for me to use. And two, we know that these are finite cash flows, meaning that I'm going to pay you $100 for the next 20 years or the next 10 years. I'm not going to pay you $100 every year forever. If I am going to pay you $100 every year forever, then I've got a perpetuity. So what do you notice? Hopefully what you observe is that we have, for the annuity formula, we've got our cash flow divided by our discount rate multiplied by 1 minus, and then in parentheses, 1 over 1 plus r to the power of t. T is going to be our total number of periods. And remember, these are always for cash flows that start next year, because whenever we do our timelines, 0 is today and period 1 is next year. With our perpetuity formula, I'm going to be paying you $100 every single year. So C would be 100, and then R is whatever the discount rate is. Now, if it's kind of hard to think about an annuity versus a perpetuity, first, let's start with an annuity, and then we can look at an example of a perpetuity. If it's a bit, we'll have examples in the lecture a little bit later, but a really easy one to think of is a stock. A stock is an infinitely lived asset, meaning there's no expiration date on a stock. And every single quarter, you expect that there'll be some dividend or some type of payout, some type of capital gain. And that's basically how you value the stock. You see the same exact thing with REITs, with essentially mutual funds that invest in real estate, where people kind of do the exact same valuation. So let's get back to an annuity. So this is the timeline for an ordinary annuity. And we'll explain the difference between an ordinary annuity and a growing annuity a little bit later. But this is an ordinary annuity. So for the next 3 years, it's going to pay $100. And we also have some interest rate. Now, there are two ways that we could approach this problem. We could do what we did before, set up a timeline, discount each cash flow, and then add up the cash flows. Or since the cash flows and discount rates are constant, they're not changing, we can apply the annuity formula. And what do we observe? Well, for a discount rate of 10%, when we do the timeline and we discount each cash flow back and then add them up, we'll find it has a present value of 248.69. And clearly, if we do the same thing with the annuity formula, we're going to get the same answer. We have to, because these are symmetric problems. They're the exact same thing. So right off the bat, pause this, work through the math, and make sure that you can find the same answer to make sure that you're doing the steps correctly. Hopefully what you can observe, at least in this example, is that if we have many cash flows, if we had 10 cash flows, it would not be feasible to sit down and do each of these cash flows separately and then sum them back up. So that's part of the reason why we love the annuity formula. We can just plug it into a very standard formula and it provides us the same answer based on the fact that it's, again, a symmetric problem. Now, in these examples, the cash flow itself has been the exact same. If we had cash flows that were changing, that were all over the place and not growing at a steady or constant rate, then we wouldn't be able to use the annuity formula or a growing annuity formula. We'd have to discount each cash flow individually. Same is true for the interest rates. If every single period these interest rates were changing, we would not be able to apply the annuity formula. We would need to discount each cash flow separately. Okay, so examples of annuities. An annuity is a finite life project that provides a fixed revenue stream for a number of years. So we'll do plenty of examples when we think about a company opening a plant. The plant will have a life of 15 years, and at the end of the plant's life, there's some expectation that the company might be able to sell it for spare parts or something like that. So over the 15 years, it's essentially an annuity. A great example is like a mortgage. You have 30 years, you're going to be paying back your house, or another example would be a student loan. These are all examples of annuities. They have a finite life, you pay them back incrementally, and then once it's done, it's done. Examples of perpetuities, hopefully we'll have a chance to talk about console bonds when we get into fixed incomes, but a great example of a perpetuity, like we said earlier, is a stock. A stock never expires, and it's basically going to be the present value of this dividend stream that you expect to get